Stoichiometry, we're back.
Those of you that had an involuntary shake right there, I'm sorry, we'll try to hold your hand through this.
Yeah, remember this? The mole map thing. We're back to it because now we have to deal with the fact that, we've always assumed in stoichiometry we had 22.4 liters per mole. We don't anymore. So the only way to really do these stoichiometry problems is to just show you some examples. It's really not anything new. What we're going to do is we're going to marry PV equals nRT with stoichiometry. That's all we're going to do.
Yeah, and remember, the go-to always is this. In order to use an equation, you got to convert to moles.
Yes.
So that's kind of our go-to, and we're going to try a problem.
So take a look at this problem. We've got the reaction that you can see below, right? N2 plus H2 makes NH3, right?
And these are all gases.
And you can see that we were given 2.5 grams of nitrogen. It says how many liters of hydrogen are required at a pressure of 3.2 atmospheres and a temperature of 15 degrees Celsius. All right, let's see if we can figure out this problem here, Mr. Dmitrowicz. You can see it down here.
Before we do anything, though, there is something startlingly absent right now. Can you pick that out here, Mr. Bergmann?
We don't have a balanced equation.
Yeah, that's absolutely terrible, right? We can't do anything at all without a
Always
balanced
start with
equation.
it's a stoichiometry like law. It's a rule. Start with the balanced equation, and there you go. So we have grams of nitrogen, and normally I would go, I'd use the mole map and I'd go grams to liters, but here's the problem is I've got TP and I'm looking for L. So we have to convert, so walk me through this, grams of nitrogen using stoichiometry to moles of hydrogen.
Now, when we do this, it might be helpful just to set up your train tracks in advance, just so we know where we're starting from and where we're going to. If you take a look at your table, we're starting at grams on the far left side of our table, right?
Yeah.
So our first thing has got to be
Grams to mole.
Grams to mole. So we're pretty proficient with that. We've done that before. So I'm going to set this up and go, all right, there's 28.0 grams of N2 for every 1 mole of N2, and I got that from the periodic table.
Yeah. N weighs 14 times 2. Yeah.
Now, the question here, if you take a look at it, they're asking us to figure out the liters, right?
Of hydrogen.
Of hydrogen. Normally in the past, we go, oh yeah, we're at STP, and we could make this assumption, 1 mole is equal to 22.4
Doesn't work
liters.
anymore, though.
But we're not at STP, so therefore we have to use PIVNR, PV equals nRT. Remember from last unit?
Let's write that down, PV equals nRT. So we know the pressure, 3.2 atmosphere. We know the temperature, right? It's asking for the volumes, that's the question mark. So if I could find the N, game's over, R is constant. So
we have these three.
This right here is going to give us the N. We have to do some stoichiometry to find parameters. So we just have, if you look at the mole map right here, right, it's one more step. So we have just one more simple step to go. And that's from the coefficients, right? So moles N2 goes in the bottom. It's a 1 mole N2, and 3 mole hydrogen, right? Yeah. And so that's it. That's our moles. So that's N and PV equals nRT. Let me get the calculator going here. 2.5 divided by 28 times 3. It's 0.268. So that's the moles now of the hydrogen. So that's N. Well, we know P, it's 3.2 atmosphere. Good news is that's already in ATMs. Remember, liter, atmosphere, mole, Kelvin. What's this term again?
Latmas per molix.
Latmas per molix. Now our temperature's off though. We have to convert that to Celsius.
Now I kind of jammed it up here, but let's put all the information we know here on the side and write it all
Fair
down.
enough. Yeah.
We have our pressure is equal to 3.2 atmospheres.
Bingo.
We don't need to do anything with
We're
that.
happy with that.
Our volume is what we're
our
trying to
question
solve
mark.
for.
Yeah.
Our N we just
Now we know this.
figured out.
It's here, yeah.
268 moles of hydrogen. And our temperature, they're giving us as 15 degrees Celsius. Can we use Celsius in this?
No, it has to be Kelvin, right? So 15 plus 273 is 288, right?
298. Oh, 280. Sorry,
288.
you're right. Wow. Math part of my brain is not working. But there's also one other variable, and that's the R. It might be good to even write this down at the beginning, because this, liter, atmosphere, mole, and Kelvin, is what our units have to be in, and that's why we've done the conversions.
So then what we're going to do is do 3.2. I'm going to not write the units. That probably mean V equals N 0.268, 0.08206, and 288.
So we're going to say do as we don't do, because we absolutely want you putting the units in here. So even though we preach that to you, do it so things can cancel out, but in interest of space.
So I just multiplied these three terms. I'm about to divide now by 3.2. and I get 1.98.
Now, if we had kept the units in here, everything would have canceled out except for the L, and that's where we know what we've done.
So you would have 1.98 liters at, if you will, non-standard conditions. All right, so in example number 2, you can see that the equation, let's start with the equation, right? We're having zinc reacting with hydrochloric acid, and as you can see, it produces zinc chloride and hydrogen gas. Now, trick on hydrogen gas is it's H2, he's one of the Brinkelhoffs, and zinc chloride, Mr. Dmitrowicz knows, is ZnCl2 because zinc is a 2 charge and chloride is a -1 charge. Now, obviously, before we put any of the numbers and junk like that in, we've got to know what the balanced equation is, right?
Absolutely.
So, and it's not balanced.
One Zn here, one Zn here,
heavy, yeah. Mhm.
one H here, two H's
Oh,
here.
fix that, yeah.
Put a 2 here. Now we have 2 CLs here, 2 CLs here. I think we're good.
We're good, okay. Now, let's read the problem a little further. It says that we are given a 3.25 liter sample of hydrogen gas, or that was produced, I should say, right? At a pressure of 777 torr and a temperature of 13 degrees Celsius. But there's also this other little thing, it says collected over water. All right, what does that mean? We'll get to that in just a second, all right? So the question, of course, as you can say, it says how many grams of zinc reacted, right? So we're gonna figure out how many grams of zinc reacted given this information.
So just be clear here, most of the time we're starting with reactants and going to products. Here they're giving us the information about hydrogen, so this is our starting point.
Right.
In order to use an equation, mustn't we always convert to moles?
Yeah.
So of these variables, remember P, V, N, and T are our main variables. Isn't this the one variable that we're missing in this?
Yeah, we don't know moles. So
Right.
what we're gonna do is we're actually gonna do Pivnert first and then stoichiometry. In the previous problem, we did stoichiometry and then Pivnert. So this is kind of that flipped, if that makes
Just,
sense.
if we were to do it another way, let's say I were to cover all this and go, hey, I'm giving you grams of H2. Would any of you guys have trouble going, hey, I have grams of H2, convert to moles of H2, use the mole ratio to get the grams? All of us would be okay with that. This is just an alternate way of getting to moles.
So we're just gonna do PV equals nRT. So P, V, N, all the stuff we've done before, right? So our volume, is our volume good right now?
Our volume is in liters, and remember,
So check.
it might be a good idea. I'm going to put the R in here just so,
Yeah.
just so you know what the units are. Until you get solid with this, I would suggest you write this down because that tells us the units. So our liters are here. I'm going to put them into the problem here, 3.25
Yeah.
liters.
And that's our volume. The pressure is 777 torrs.
Can we use torr, Mr. Bergmann?
No, we got to convert to atmospheres. Now we've got an issue here, and that's something we need to talk about because it's 777 torr, but it said that it was collected over water. If you'll recall, if you're collecting over water, remember this is this deal, there might be 2 gases. You've got the hydrogen gas, and then you've got a little bit of water vapor pressure. And so when we look up at the table is 11.2 torr. So the total pressure is 777. So all we have to do is subtract out the number from the water vapor pressure table, 11.2.
Confused myself. 11.2 torr. There's also something else here. This is both in torr. Now if we subtract this out, 777 subtract 11.2, we're gonna end up with 767 766.8, correct?
765. But yeah, so let's just go 7, because it's only got a digit here, we're going to round this whole number. So it'll be 766.
I'm going to put this down here because I did not have enough space here. So 766
66 torr.
torr. That is actually the pressure of just the hydrogen gas in
Yes.
here once you subtracted out the water vapor.
So now we simply divide by 760, right? Because it's a slightly over 1 atmosphere. It's 1.01.
What is it?
1.01. So our pressure is now 1.01 atmospheres. And equals N, and times R. R is a constant, so we can just maybe slightly down here, right?
This is what happens when you don't plan on your
Space.
location, yeah.
And the moles, or the temperature is 13, but we need to add 273 to that. So that'd be 286, right? So now we can solve for N. Now we're not done yet, but we're gonna, I'm gonna multiply the things on the left and divide by the things on the right. So 1.01, oops, type it in right, 1.01 times 3.25 divided by 0.08206 divided by 286 gives me 0.140. And that's moles of what? Hydrogen gas.
Just in case you're wondering, for canceling purposes, we have ATM here, ATM here, we have L here, L here, we have K here, K here. Our moles, it's 1 over mole, which is the same as having a mole flipped, divided by reciprocal. But this is our number of moles.
So now we do stoichiometry. So now we go back to Mr. Mole Map, and we're starting at moles. So we're starting in the middle of the mole map table, right? So we're going to say 0.140 moles of H2 over 1, and we want to convert to the grams of zinc. Now the first step, of course, is we have to convert mole to mole ratio. Now this is an easy one. It's a 1 to a 1 ratio. So 1 mole of hydrogen on the bottom. Hydrogen on the bottom because it's needs to cancel the hydrogen, and then 1 mole of zinc. And then we're going to convert to cancel out the moles of hydrogen. And now the molar mass of zinc is 65 grams in 1 mole. Forget the decimal, 65 point something. Do you have it off your head, Mr. Dmitrowicz?
I do. When I look at the periodic table, I think it's 65.4.
65.4. And so we're just going to take 0.140 times 1 divided by 1 times 65.4. 9.15 grams of zinc. So let's think this question. Let's kind of rephrase our question. If you have all this information, the volume and the pressure of the hydrogen gas that you produced, how many grams of zinc did it come from? 9.15.
And again, another way of looking at this is all this information right here, in the past we give it to you like grams.
Yeah.
It's just a more complicated way to end up with the moles. But once you're at the moles and you can use the stoichiometric flow chart, we're in good shape. It's going to take a little bit of practice. Let's be really clear.
And you've got quite a few problems you're doing in class. We've got some labs to do. It'll all make sense when you're in class. Catch
You
you.
guys have a blessed day.